Let's talk about missing data and how to use R to handle and understand missing data. So one thing that you'll notice is that whenever you are dealing with columns that have missing values, some of the functions you're used to running, like mean, median, etc., will no longer work. In fact, you'll get an NA out as a result. Let me load up the air quality data frame, one of the data frames that R knows about naturally, so we can get it in there just by using the data command. If I try to run the summary of the air quality data frame, I can look to see that there are 6 columns in the data, and the very last row of the summary for 2 of these columns say that we have 37 NAs for each of them. Now, why is this a complication? Well, if I try to, say, take the sum of all of the values inside the ozone column, I get an NA out, even though there's a lot of legitimate values in here. Or if I were to take the mean, I'm going to notice that I get the same issue. I have an NA even though there's plenty of values that are present. So when you are handling missing values in a data frame, you need to be careful about how you set up those summary functions. Now, the key thing is to make most of the functions you know and love work, all you have to do is add in an additional argument to ignore or to omit those missing values, and that's to add in na.rm equals true. So if I say mean of air quality $ozone, the average of the values in that column, with an na.rm equals to true, that strips out the NAs and then takes the average of the results. And the same thing with the sum function. So if you're calculating the average, the median, a quantile, etc., and you're expecting a number to come out because you know there's legitimate values in there, but you get an NA for the result, that's an indicator that, hey, you have missing values in your object. So how do we know how many missing values? How do we explore the extent of missingness in a data frame? Well, I think really the best idea is to start out with summary. Summary is always going to tell you how many missing values there are as the very last row in summary. So we see ozone and solar radiation having 7 and 37 missing values each, while the remaining columns don't have any missing values at all. So that's a nice way to do it. There's also a shortcut for if you just want the number of missing values for each column. And that's using an advanced command called lapply that we're not going to use all that often in BAS 474, but it's a neat function to work with. So what lapply does is it goes through each column of a data frame and calculates something about it. So this function right here, lapply air quality, and then this function right here is basically going to sum up the results of running is.na, so sum up the true and falses associated with that function. Essentially just count up the number of NAs that are there. Lapply will do that for each column in the data frame. Now the output's really long, so to make it not as long, we use unlist. The reason for that is a little bit more advanced than what we want to be talking about right now. But this command right here lets you know each column and the number of NAs that are in each one of those columns. So all you have to do is replace this by the name of your data frame, and you can quickly see how many missing values are there, which is just a complement to summary. It tells you the same sort of thing. Now, how do you know the total number of missing values in the data frame? Well, you could add up manually each of these NAs, or you could just say, well, what's the sum of running the function is.na on the data frame in question? So 44 total NAs, that's 37 plus 7 here. What's the average number, or the proportion of NAs in the data? Well, we could ask for the mean of this vector. The mean of a bunch of trues and falses tells us the proportion of trues that live in that vector, so it looks like about 5% of all the data values in the air quality data frame are missing. One other example, let me read in the dozer data frame, and we have 1,000 rows of information about bulldozers being sold at auction, and there are quite a few NAs. Now, a lot of these NAs are in the form of blanks in categorical variables. Let me just isolate myself to just the 13th through 15th column. If I look at the levels of this categorical variable, one of which is a blank. So pair double quotes, nothing in the middle. That's its representation as a missing value, but it hasn't encoded it as an official NA like what R likes to treat stuff as. So these 3 commands just simply replace the blank level with NAs, so that now if I were to look at a summary of these 3 columns, it lets me know how many NAs are there. All right, so how do we deal with NAs? Well, we've already talked about one way, adding in that NA.rm equals true to common functions like mean, median, max, etc. There's a way to actually completely strip out all of the NAs so that you can work with just the complete cases going forward. And to no big surprise, the command is actually called complete.cases. So let's imagine that we're going to deal with the air quality data frame, and specifically, let's let the x variable be the ozone column of that data frame. Lots of NAs in here, and we know that, okay, if I add in NA.rm equals to true, I can calculate the average of the values that do exist. But let's imagine I just wanted to get rid of those NAs entirely. Well, if I run complete cases on that vector, I get a bunch of trues and falses out. True for if the value is there, false for if the value is missing. And so what I can do is I can just use the locations of where I see trues here to let me know what elements I would like to keep. So doing something like x left arrow x bracket complete cases of x is going to overwrite the values in x with just the values that are present. It's going to strip out all those NAs. Now this is irreversible. We can't put the NAs back in here. We can't undo this command. So in general, we don't use complete cases all that often. But it is a way to permanently strip out the NAs from a vector. So you can also use complete cases on a data frame. So if I look at that air quality data frame, I see that some rows are complete, have information for everything. Some rows have missing values. And what complete cases will do for a data frame is it'll let you know if all of the values are present or if at least one of those values is missing. I'm trying to scan through and look for a row that has 2 missing values in it. Row number 27 has 2, row 26 has just 1, row 28 is complete. So you'll notice if I run complete cases on a data frame itself, it's actually going to return true and false depending on whether or not the entire row is complete. So air quality 26 through 29, we saw 1 missing value, 2 missing, complete, complete. If I run complete cases on that part of the data frame, I get a false, false, true, true. False if at least one of those values is missing, true for if all of the information is present. So what if we wanted to strip out all of those rows in the air quality data frame that had at least one NA? Well, here's a command. We can use which case or complete cases once again. If I ask which complete cases air quality equals to true, that lets me know the row numbers where I have complete information. So if I slap that inside of the square brackets, put that to the left of the comma to refer to the rows of the data frame, I can essentially just extract out the rows of the data frame that have complete information. So air, left arrow, air quality, all of this stuff is going to make it so that all of the resulting rows have complete information. We see that there's no missing values. All right, so those are some quick and easy ways to handle missing values when you deal with them in data frames. Summary is really good for seeing how many there are. That lapply command very quickly tells you the number of missing values for each column. And then knowing about the additional argument na.rm equals to true will allow you to run most of those common functions where you're summarizing data to run without issue. Now, when we're doing data mining, sometimes it's actually quite interesting to understand why there is missingness, what sort of patterns might exist. If we have a missing value in one column, are we more likely than not to have a missing value in a related column? So very often we dive into the extent of missingness a little bit more closely, and there's a few tools that we can use in R to explore if there are or are not any patterns in the missing values. One useful library is the mice library, and what we can do is load that up after it's been installed and to run the command mdpattern, missing data pattern. Now we saw when we ran a summary of the air quality data frame that just the first 2 columns had missing values, 37 and 7 respectively. So why don't I run the mdpattern on just those first 2 columns? Slap a square bracket after the name of the data frame, put a comma in the square brackets, leave the left blank, so all rows, after the comma, 1:2, so we're just looking at the first and second column. When I run this, I'm going to get 2 bits of output. One, a graphic, and another, a text output. Let me talk about the text output first. Basically what it's doing is it's telling you everything there is to know about missing and complete data for each of the columns of the data frame that you ran the command on. So we're just dealing with the 2 columns of the air quality data frame. And what we see in these 2 columns are 1s and 0s. Now what a 1 represents is a value being present. So this 1, 1 here represents a row, essentially, or rows, where I have values for both solar.r and ozone. This number to the right tells me that there's 0 missing values associated with this pattern, and a total of 111 rows that have complete information with these 2 values for solar radiation and ozone. Moving on to the next row, I see that this is representing a pattern where I do have solar radiation, but I am missing ozone, for a total of 1 missing value in that pattern, the number to the right here. Looks like 35 rows have solar radiation but are missing ozone, 5 rows that are missing solar radiation but do have ozone, 1 total missing value in that pattern, and 2 rows that are missing both. And if I look at the numbers all the way down here at the bottom, 7 rows that are missing solar radiation matches up. 37 rows that are missing ozone matches up, and 44 total missing values overall. So I can quickly see how often pairs or combinations of values are missing together or just by themselves. Everything I need to know about the patterns can be learned from the output of MD pattern. This is just a visual giving you the exact same information. Blue basically means present, reds means absent. To the left tells you the number of rows that have that pattern. To the right tells you the number of missing values associated with that pattern. At the bottoms tells you the total number of rows missing, solar radiation, ozone, and then the grand total of 44 right over here. Now that's kind of interesting, but we might like to take that a step further and say, okay, well, is there a bona fide association between one value and another being missing? Let's say if I know that a row is missing ozone, does that make it more likely or less likely that that row is also going to be missing solar radiation? Now, there's a whole package to study association rules like this, and that is in the A-rules package. And we can run a few lines of code to do a formal analysis of missing data patterns. Now, you're going to keep this code as is always. You're basically just going to left arrow the name of the data frame that you're interested in conducting this pattern analysis into an object called data in all caps, and you'll essentially run this chunk of code verbatim. And there's 2 bits of output that we are going to focus in on. The first is the output to the command item frequency. This goes through, and for every column of the data frame that we're looking at, it tells us the proportion of rows that are missing values. So ozone is missing values in about 24% of the rows in the data. Solar radiation missing about 4.6%. None of the rows for wind, temperature, etc. are missing values. So this kind of gives us the baseline proportion of rows that are missing values for each of those columns, or what we're going to refer to as kind of the prior probability of those columns missing data. The prior probability of a row missing solar radiation is about 4.6%. Prior probability is just the overall probability without any additional information thrown into the mix. Now the output of rules, inspect rules here, is really interesting because it dives into a little bit more detail what associations exist between the presence of missing values. Now let's break down what this first rule is saying. So we have a left-hand side to the rule and a right-hand side to the rule, LHS and RHS, and it's important to know how to interpret both these quantities. Basically what we can do is we can say the right-hand side is talking about which value is going to be missing that we're studying. So if we want to know something about the probability that ozone is going to be missing based on whether or not solar radiation is present or missing here, well, here's the rule for us. Here's how we read this rule. If solar radiation is missing, then ozone is also missing. So if we know something about solar radiation being missing, we're going to know something additional. We're going to be able to update the probability of ozone being missing. How do these numbers come into play here? Well, the way that we're going to interpret these numbers is as follows. And I want to refer to some of these notes here. A lot of these slides deal with imputing or guessing what the missing values might have been. We're going to worry about that at a later time. All right, so how do we interpret some of these numbers here? So I have an underlined phrase that you're basically just going to copy paste and update to make the context relevant to the problem that you're studying. But essentially what we're going to do is, for this rule where we're talking about the probability that ozone is missing, once we know that solar radiation is missing, we're going to interpret it by referring to the probability that ozone is missing just overall, the prior probability of ozone missing, and the factor by which that probability increases when we know solar radiation is missing as well. That's actually what the value in this column called the lift is telling us. It's the factor by which that probability increases once we know that this guy is missing as well. So here's what we can say. The probability that ozone is missing in the data goes from about 24% overall up by a factor of about 1.18 to 28.6%, the confidence, once we know that solar radiation is indeed missing for that row. Now the second row is kind of looking at that association the other way around. What we can say is that overall 4.5% of the rows are missing solar radiation. However, if we notice that that row is missing ozone, that probability increases by a factor of 1.18 up to a probability of 5.4%. So if we know that ozone is missing, the probability that solar radiation is missing bumps up from 4.5% up to 5.4%. If we know that solar radiation is missing in a row, the probability that ozone is missing goes from 24.2% up to 28.6%. So these probabilities of missingness increases given the knowledge that some other quantity is missing. We'd like to know if that increase is statistically significant, because we expect to see some patterns just by random chance. There are some tests of significance that let us know whether or not that increase in probability is readily explainable just by happenstance, or if it's indicative evidence of a real association going on. And that's with these last two lines here. And what we're going to do is look at these numbers and then more carefully look at the output of the is.significant command. Now when I see true here, that indicates the association is statistically significant. That bump up in probability of that quantity being missing, once we know the other one is missing, is not readily explainable just by chance variation. It's more indicative of an association. The fact that I see false here says that, okay, sure, the probability of solar radiation being missing goes from 4.57% up to 5.4%, but this increase is just readily explainable by chance variation. It's not really indicative of there being a real pattern going on here. I don't have much evidence that this is a very bona fide association. And likewise, sure, the probability that ozone is missing goes from 24% up to 28.6%, but that sort of increase is readily explainable just by random chance. The fact that I get a false here says that, nope, that's not a statistically significant association. A little bit more practice here. Let's do this for part of the bulldozer data frame. What I want to do is I just want to look at the three columns that have these three quantities. Something about the model of the bulldozer that was sold at auction. A whole bunch of NAs here. Are there any interesting patterns that we can talk about? Well, let's left arrow the name of this data frame into data and run this code verbatim. And let's talk about some of these rules. So I'm going to pick out this one just because, and let's talk about it. All right, so the right-hand side of this rule is talking about FI model series and the probability that it's going to be missing in a row. Now, what we know is that overall, 87.3% of the rows in this data set are missing this value. That's a huge fraction of rows that don't have this. Now, what this association rule is telling us is that the probability that FI model series being missing goes from 87.3% up by a factor of 1.025 to just about 90% if we know that both of these quantities happen to be missing in the row. So if we know that FI secondary description and FI model descriptor are both missing in that row, the probability that FI model series is also going to be missing goes from 87.3% up to just about 89.5%. Is that a statistically significant increase? Well, we can go look at the result of these two commands. This was rule number 7 that we just analyzed right here. 1, 2, 3, 4, 5, 6, 7. No, that sort of increase is not statistically significant. That increase is just readily explainable by chance variation. We expect some patterns to be there just by happenstance. This looks like it's probably one of them. Notice, however, that Rule 6 is statistically significant. What does Rule 6 tell us? Well, it's telling us that the probability that FI model descriptor being missing goes from 82.8% up by a factor of 1.021, this guy right here, to 84.5% when we notice that FI model series is missing in that row. So not a huge increase in probability, 82.8% up to 84.5%, but in this case, the analysis is suggesting that this increase is statistically significant. Looks like a reasonable amount of evidence that there is an association going on. If we know that FI model series is missing, well, that tells us something additional about the probability that FI model descriptor is missing as well. So these are some of the things that we look at for missing value patterns. If there are patterns in missing values, then we can exploit that when we come up with intelligent guesses. A big section of the notes talks about missing data imputation, and there's a lot of good tools in R for doing this. The MICE package, the MISForest package, HMISC, etc. And there's some additional resources listed on the Canvas side as well. We're not going to have the time in this class to go and actually get practice kind of getting intelligent guesses for missing values, but it's something that you might end up doing in the real world. Very often your models can improve if you come up with an intelligent guess for a missing value. And that's typically because when we are doing data mining, building a predictive model, trying to predict something about new customers or something that's going to happen in the future, it turns out that even a relatively bad guess for a missing value is better than no guess at all and just kind of throwing away that row or throwing away that column because it's missing values. So when we can come up with a good guess for missing values, we should do it, and understanding what patterns exist behind the missingness of different columns of data is a good place to start in kind of how to come up with an intelligent guess.